Okay. Any question from previous class? Any? Anyone to discuss anything about first week class? No? Okay, never mind. Maybe I will continue to complete lecture 2, still in the chapter 1. Okay, before we start our class, I would like to maybe about something related to the air distribution. Yeah, maybe I would like to ask a pop-up quiz about this figure that illustrated in this slide. So, based on the picture at the right, explain the statement. A fan creates the higher pressure. The open end of the duct has a lower pressure, so that air flow out. So, anybody or any from you can tell us this statement, yeah, regarding to the pressure that produced in the from the blower or fan until to the diffuser or end of the duct is lower. Anybody can explain?
Maybe the fan force the air to flow in.
Yeah. Anybody? Any else? Maybe from the other idea? Give me how the fan can create uh, high pressure,
Different
huh? And then
pressure from the starting and the end of the duct cause the air flow out and it come with the help of the fan.
hmm, okay. Any else? Maybe can relate to uh, the principle of theory or law, maybe.
The higher pressure, the air will flow from higher pressure to lower pressure.
Yes, correct. This one, what I want. So actually, we use from previous lecture class, we already introduced the uh, Bernoulli principle that provide in the duct system or piping system. It mean in the point from the point to point, other point. So from the point first, maybe from the fan, and then the other point is we to analyze is end of the duct system. So it's mean from point one to point two, consider as the end of the duct. And then what happened? If we relate to the Bernoulli principle, mean we have to condition of a pressure to allow the air to the flow, to flows, yeah, to allow the air to flow. So based on this Bernoulli principle, we have three uh, properties should be considered, yeah, to give air giving the flow. Okay, based on the figure illustrate, maybe Z, yeah, maybe Z is a small elevation differentiate, so mean maybe contribute in small or insignificant in the uh, elevation differentiate. Yeah. So let's check the Bernoulli principle. We have the P, we as pressure, and then also we have other properties, kinematic. Energy. Uh, yes, energy kinetic. Energy kinetic, and then also energy from the potential. Yeah. So because of some of these properties, yeah, we can allow the uh, flow in the duct system. So because of we need, yeah, to transfer the air from the other point to the other point, so mean we should be give a high pressure to low pressure to allow the air in the system. If not, we should be give the velocity. Yeah. So based on the question, yeah, the question is the focus on the pressure. So we mean that the fan is will be produce the high pressure, but the end is will be low pressure to allow the system of airflow. Yeah. So that's why we need to produce the high pressure in the first point. Yeah, first point consider as a fan. Yeah. So that's why the statement a fan create the high pressure to allow to create the flow system. Gitu dia. So ada soalan? Kenapa? Ada lagi? Ada soalan? Atau nak bagi statement? Tak ada.
Tak ada, sir.
Tak ada. So back to the Bernoulli system principle. So you can ask for from there. Okay. Now we back to the airflow system formula. Principle of airflow. In order to design proper forced air distribution system, is required to have a good understanding about how air flow in the duct, what factor affect airflow and flow design. So airflow caused by a pressure differential. I just mentioned before, between 2 points. Flow will originate from an area of high pressure and process to area of low pressure. Okay, this one. Okay, based on the Bernoulli principle that developed by three part of condition. The first part is considered as pressure, and then the second part is kinetic energy, and then the last part is potential energy. So because of these properties allow a duct system to give the flow. Okay. Okay. In the first statement mentioned about this one, about the pressure. So this one we can illustrate like the. Okay, we have gas, maybe gas tank, with a high pressure inside here. So we call P tank. and then the outside is a P atmospheric, yeah, pressure. So if the tank have a hole or leaking here, and then because P tank is higher, yeah, compared to P atmospheric, so what happened? So the pressure will be come out, yeah, to the outside. So then the flow will be happen. So this one is only example differentiate of pressure. And we can also allow the flow happen in the system by kinetic, yeah, energy, and also by potential energy. If involving in the system is both all the properties, yeah, so make a strong flow in the system, yeah, even though only one part act in the system, can access the flow. Dah boleh dah, satu part saja sudah cukup, is enough, consider enough. Even though only one part, yeah. Can you imagine if we contribute all part, yeah, in the system? Okay, that's how the Bernoulli work. A dark air moves according to the three fundamental principles: physics, conservation of mass, conservation of energy, and conservation of momentum. Yeah, the dark air move according to the three fundamental. So we have a mass, yeah. Mass is considered maybe a fluid of mass. Conservation of energy, yeah. As we know, when we transfer the air, yeah, we will be involving the energy from the electrical energy, and we convert to the mechanical work, and then mechanical work will be produce the airflow. And then conservation of momentum is, as we know, every mass, yeah, will be give the produce the momentum from the velocity, yeah, every mass. So that's why some, yeah, even though meet the like the junction, yeah, or the elbow will be give the energy, yeah, to the next the junction, yeah. Even though have the what do we call a friction from their instrument. Okay, in the conservation of mass, mass is neither created nor destroyed. So mass cannot be lost, mean in the system. Yeah, as long the system is no leaking, so mean no mass cross the system. Yeah, as we know, the system should be boundary, have the boundary to avoid mass crossing to the environment. From this principle, it follow the amount of air mass coming into a junction in a ductwork system is equal to amount of air mass leaving to the junction. So we already learned about the mass balancing, yeah. In the maybe from the previous subject like the thermodynamic. So M1 should be similar to the M2. So same when we convert to state to the mass flow rate. So it should be similar within the first point to the second point. In the most cases, the air in the duct is assumed to be incompressible. An assumption that overlook the change of air density that occur as a result of pressure loss and flow in the ductwork. So to be maintain the density, we should be considered incompressible. As we know, the formula of density is m over to volume. If we maintain the volume, so mean the density will be maintained. Because volume compressible, mean volume 1 is volume 1 equal to volume 2 if incompressible. Incompressible. If we compress, mean we should be reduce the if we consider the compressible, mean the volume is reduced. Okay, in the duct work, the law of conservation of mass mean a duct size can be calculated for a new air velocity using the simple equation. Okay, back to the formula of the V dot equal to VA, while A is considered the area. So mean if the area is circle, so to be in the area is pi. Let's consider as D. So mean when we talk about the amount of the volume rate, this one is volume rate. So mean the V1, consider this one is 0.1, and then if we go to 0.2, to be similar, because we try to maintain the volume rate. Then just elaborate here. Okay. So if we ask V2, just remove A2 to the left side. Okay, sorry. Okay, so where V is velocity and A is a area. Okay, now we going to other part is law of energy conservation. Energy cannot disappear. It's only converted from one form to another form. As mentioned before, when we try to run airflow, maybe we need to convert electrical energy, to the mechanical work. Yeah? And then from mechanical work, we try to heat transfer. So that means we have three of energy uh, converted. Yeah. Bernoulli's equation in its simple form shows that for an elemental flow stream, the difference in total pressures between any 2 points in a duct is equal to the pressure loss between this point. Okay, actually, in the Bernoulli, because we analyze, between 2 points, so mean from the left side as first point to the right side formula as second point should be a balance. So if not balanced, something have in the uh, maybe head loss. Yeah, maybe head loss we consider as a head loss. A pressure loss, yeah, uh, between point 1 and point 2, yeah, is calculated by total pressure in point 1 and total point pressure 2. So this differentiate we call as pressure loss. Okay, now we go to conservation of momentum. A body will maintain its state of rest or uniform motion unless completed by another force to change the state. Yeah. Okay. Mention to the state. Yeah. Mean relate to the uh, a motion. Yeah. It's not relate to the phase of the fluid. So as I mentioned before, momentum is related to the mass and then related to the uh, velocity, kinetic energy. So between this condition, yeah, because of the we have a mass and then velocity, yeah, something happen from differentiate of the velocity. This law is useful to explain flow behavior in duct system fitting. Yeah, fitting is instrument, yeah, instrument in the during along duct system. Okay, we already learned about this type of the flow. Yeah, we have the laminar and turbulent. So maybe yeah, from fluid mechanics we can identify by coloring toner during the uh, water flow. Yeah, easy to us to identify whether the laminar or turbulent. So actually I ask you, what is the drawback of the turbulent flow? Any idea from you? Huh? Hello? Eh, Ada orang ke tak ni?
Ada, sir.
Okay. Actually, what happened if uh, the airflow system will be produce turbulent flow? Apa yang terjadi?
Flow rate turun.
Correct. It's not flow rate turun, tapi effect flow rate. Uh, correct. Flow rate.
Dia macam keluar angin dia rendah kan. CFM dia kurang. Reduce.
Reduce.
And will be other vibration.
Vibration, correct. Yeah. That's why we try to maintain in the laminar flow. So vibration correct, pressure turun correct, and then the velocity turun sebab it should be the velocity we will produce in the certain point because of turbulent. It's not in the nice flow to bring the thermal. So that's why we try to avoid the turbulent flow. So what we need, we try to understand first the type of material what we use in the duct system. Is it considered smooth? And then if not smooth, how much the diameter minima should be developed. Macam gitu. So, how many how much Reynolds number for consider laminar flow? Still remember?
1000 hingga 2000. 1000, 2000.
Yeah. 20,000. Below 20,000 is considered laminar. So between 20,000 to 40,000 is consider intermediate. Not intermediate. What the phase within the turbulent flow? Apa namanya? What another phase before turbulent?
Transition flow.
Intersection flow, correct. So, and then once get 40 above, 20,000, 40,000 above, consider turbulent flow. Okay. Flow parallel to a boundary layer in hatchback system, the plenum is a duct. Flow parallel to a boundary layer. Okay. Actually, when we look into the laminar flow, every layer will be similar velocity. That one consider laminar. But when turbulent, we look by layer, mean inside duct, duct system, we can check layer by layer. So in the turbulent flow will be produce different velocity. That's why will be got the turbulent flow. Flow which is perpendicular and near the center of the duct and parallel near the outer edges of the duct. Most hatchback application fall in the transition range range between laminar and turbulent flow. Actually already informed in the text, the transition range. Okay, now we go to discuss about the friction effect. Okay, and friction effect, friction loss, head loss, is the reduction in the total pressure, pressure drop, pressure loss due to the friction of the air moving through a duct. The friction loss depend on the shape of the duct, not only from the material itself, but also from the shape. In straight section of the ductwork, the loss in the static pressure due to the friction flow resistance in the duct as a result of air turbulence and the roughness of the duct. A static loss of the straight section duct can be calculated by using the following formula for a given length and friction factor. So this one is based on the 100 feet long in the head loss. So the formula HL is L times 2CL 100. L is length of the straight section feet and CL is the friction factor for 100 feet of the duct. Determined through a friction chart or a duct calculator. So we can check both using the friction chart or the duct calculator. So anybody have seen the friction chart or duct calculator? Maybe familiar with duct calculator. Ada yang pernah tengok duct calculator?
Pernah, tapi tak pandai guna.
Oh, tak pandai guna. Okay. Nanti kita try ya. Saya ada ni. Topik ni pun ada. Kita discuss kat sini. Ya. So nanti akan kita tengok. So information dia. Dia ada air volume design. And then we have also type, shape type of duct system. Kita nak pilih apa. And then the velocity, air volume, velocity, then also rectangular duct. So we have 4 parameter inside of the duct calculator here. Boleh nampak? Okay. Okay. Dynamic losses include losses due to change in the direction of the duct and change in the cross-section area of the duct. So you can see dynamic loss. First maybe in low elevation and then we come to high elevation. From this condition will be contribute in the head loss. Then we call dynamic losses. You can see the first we use 90 degree of elbow and the second is 45 degree of elbow. And then another is contribute by suddenly enlargement or suddenly contraction. So this instrument also contribute in the head loss. It's total loss. Then we can total losses by instrument will be add or sum in one final head loss. Okay, dynamic losses are calculated from the velocity and a loss coefficient for type of the duct fitting or transformation, sudden enlargement or sudden constriction in the area using the following equation. Actually, by Bernoulli equation, also we can determine the losses. Mean the pressure, based on the pressure, based on the velocity, we can measure and then we can decide how much the losses happen during the airflow. Okay, by calculation, also we can write for dynamic losses. HL equal to C to V is velocity. This one is by velocity over to 4005 square. C is dynamic losses coefficient for type of the duct fitting or for transformation. So they will be given by table, yeah, and then we can use the C. And then for V, we can measure the V velocity, and then we can analyze the head loss. Okay, this one is duct fitting. Duct fitting commonly used in the HVAC to change the direction of airflow, and there are more than 220 types of duct fitting database developed by ASHRAE. So quite big number, yeah, in the type only, yeah, for duct fitting, 220 types. Yeah, every type will be contribute in the losses. The most common and standard duct fitting type is round or rectangular duct elbow with typically angle of 90 and 45 degree, and radius of curvature. Okay, how to define 45 and 90 is like this, yeah, based on the angle. Okay, this one you can see, yeah, this one mean in the 90 degree. Okay, this one is a round elbow. Maybe if we compare, yeah, this one is consider the smooth one, and then this one is consider 45, yeah, consider 45 degree. Okay. It's convenient to determine the dynamic losses coefficient for the round duct fitting through the following equation and by assistance of the following table. So you can see the table C, yeah, this one will be contribute in the coefficient of the losses, C, yeah. C prime is the coefficient for 90 degree elbow. This one is for C prime, only 90. So K theta is the angle correction factor. So maybe we can consider K theta for 90 degree is 1, I think. Yeah. K theta, yep, yeah, this one. For 90 degree is consider 1. For 45, consider K theta is, but C prime only mention on state to 90 degree. So comparison, ratio within the this one is comparison with the diameter. R is the D is diameter, I think. Yeah. This one is ratio inner diameter, inner diameter. Yeah, D. Okay. Dynamic losses that results from transformation can be calculated by identifying the ratio of entrance area to exhaust area. The design angle theta with respect to the following table. Or mean that one is compared to input ratio input to output. Okay, this one D0 to D1. This one is a reducer or for suddenly large, this one. Over there, this one. So enlarge. Loss coefficient for transition. So compare by ratio, area. So we can see the ratio. This one. Then the theta. This one. So we can choose based on the design. Okay, before we go to the friction chart, any question? Ada soalan?
Tak ada, sir.
Okay. Okay, let me take 5 before I continue to next slide. Boleh
Yes, sir. Boleh, sir.
Okay, okay. Okay, let's go. We try to continue to complete this lecture class. Okay, now we go to the friction charts. Okay, the friction chart is a chart diagram that shows the relationship between the airflow rate, static pressure drop, duct size, and air velocity. So this will we get the information from the friction chart, how we design the duct system, and then will be guide us the proper size, yeah, to avoid unwanted like the high head loss. Yeah, so that's why they develop a friction chart based on the their research. Yeah, actually we are already only use because this one is already mean the uh, good in the testing already, because this one is already got from the research. Yeah, it's not developed by only one person, but this will developed by certain researcher, and then we just use it to make easy to us in designing. The purpose of using friction chart is to find a duct size when two values are given. So how we plot the chart is based on the two parameter, and then this two parameter will be got the intersection line, and then from there we will get the two other of a parameter like duct size, yeah, and also what else? Duct size, and then the I forget. We will check later what information. To find the round duct size required to provide an airflow at given static pressure drop, apply the following procedure. Okay, how to plot? Locate the airflow rate in the unit CFM on the bottom of the chart, and locate the static pressure at the left side. Yeah, water column, yeah, per 100. Yeah. Locate the size of the duct and velocity at the intersection of two lines. So we will get the uh, proper size of the duct. Okay, let's check. Okay, this one. Okay. Have you seen the friction chart before? Have you seen? So let's check what we have here. Okay, in the y-axis, yeah, in y-axis we have friction loss, yeah, inches of water, every 100 feet. Yeah, so this design is every 100. So every 100, 100. And then on the bottom, air quantity in the CFM, yeah, unit. And then what else? Okay, in diagonal on the right side, yeah, we have in the velocity, yeah, FPM here. Tap, 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 tap. Yeah. And then in diagonal, in the this one is uh, duct diameter. So we have four information in the friction chart. Okay, and then if we plot intersection, at least we have two information. Let's see. Uh, let's say we have 0.2 of friction, and cross section air quantity is 1000 CFM, and then we can design. This one is for duct, yeah, duct diameter. We can choose in the duct diameter is around here, maybe below 12, yeah, maybe around 11. It's not 11, 11 something of diameter. Okay, This one. So this one is maybe close to 12, yeah, duct diameter. But for the this one velocity, we have several optional. You can choose, yeah, what the velocity we need to design along this diagonal. So maybe we can choose 1,800 velocity or 2,000 velocity in the FPM. Okay. Any question? If you still confused how to using the friction chart, ada soalan?
Okay, sir.
Okay, that one is true. How about other? Boleh tak?
Boleh, sir.
Boleh, senang je kan? Yalah, siapalah kita kan? Ya. Senang ni. Okay, is don't have question here. Maybe we can proceed to yes, to duct calculator. Okay, this actually the actual duct calculator. So what information we have here about before that we read the text first. Duct calculator is a tool used to determine the round duct size, shape, and convert into the rectangular or square size. So from the from the round duct to the convert to rectangular square. Once it's a known at least two parameter value such as the air quantity and air velocity. So at least we have two parameter, air quantity and the air velocity, or friction loss and then air quantity. So we can plot between this, whether with the plotting air quantity and air velocity, or we can plot from the friction loss and air quantity. So you can choose what information you have here. Okay. Okay, which one the air quantity? Yeah, air quantity, this one. Yeah, friction loss, yeah, here. So, friction loss and air quantity, this one. If you choose this one, you use this one. Okay. If you choose okay, I mentioned this first. Okay, we choose this one. Then you can choose this one. So from this intersection, this not intersection, a matching. So this one is really match. For example, matching. So until to match, for example, what you need to design. I say this one is a friction loss is 0.5. Will match to air quantity what? So just remove, okay, like this. Oh, nah dia. Okay. Okay. Tu. You can see or not?
Tak boleh, sir. Boleh,
Kalau
boleh, boleh.
tengok, boleh. Dia
Tapi kecil.
kecil, dia can motion, and then you match, matching the line. So design dia berapa? How much you design the friction, and then match to the air volume, match by the line, matching like this. Okay, from this matching, you can see the rectangular duct. Berapa? Okay, match. Match tak? Match. Aduh mak, oi. Dia akan match kat sini. So dia akan match dekat sini. Tu mana ni? Okay, once you match here, by your designing, and then you can see here which line matching. So this one is a rectangular, this one side by side. So matching dia kat mana? So for example, which line matching? This one. This one is width with the 50 inch by I think 70. Yes. No, this one is 26. Yeah. 26. So this one is maybe by 26 size inci. So macam gini lah. Maybe and 26. Yes. So by this intersection, and then if you refer other, same thing. You mesh this one, and then you can get this one. So the product is this one. Or in the round duct you can see here. Kalau nak round yang bulat kan, so roundnya yang ini. This round duct. This one is rectangular. Duct. Okay. You get me? Do you get what I mean? Boleh
Boleh sir. Sir, yang duct punya dia punya size tu boleh nampak dekat yang calculator tu ke?
Boleh nampak. Yang ni yang ni ni clear. Kalau ini tak nampak sangat nombor dia. So duct ni ada dijual murah je. Dia kertas je. Just paper, so maybe hard paper. This one is hard paper. So we can see whether round diameter or with the rectangular duct. So based on the floating quantity air velocity or friction loss and air quantity. So this one we can get from the friction chart. Yang ini boleh dapat friction chart. So kita nak design macam mana? Okay. If okay, I can proceed to next slide. Boleh
Boleh sir.
Okay. Okay, density and the altitude effect. Actually, the air will be influenced or affected by the elevation because the pressure will be varied. As we know, different elevation will be effect to the pressure, and pressure will be effect to the density of the air. Okay. The air density is defined as a mass per unit volume. It is affected by two factors such as temperature and elevation above sea level. So both will be influenced to the density, temperature and elevation. The standard air is defined as clean, dry air with a density is 0.075 pressure per feet cube, pound per cube foot. And 1.2 kg kilogram per meter cube, with the barometric pressure at sea level of 29.92 inches of mercury, or similar to 101.020 kilopascal if we use the SI unit, and the temperature of 70 degree Fahrenheit or 21 degree Celsius. Ni standard in that condition. So different temperature, different elevation will be change. Ini tahu kat mana? Where is this location? Any idea where is this location? This pressure?
Sea level.
Sea level, correct. Yes, exactly correct. So if we change the elevation to higher, so the maybe temperature change, pressure change, and density, density of the air. Ni yang paling penting. Will be change. Okay, next. In case of the condition of there, in case of the condition other, then standard air is recommended to adjust static pressure multiplying density correction factor, which is found from the table. So if not in the sea level, so what we do is go to the third condition ni lah. Third condition ni. So density correction factor, and then calculate to adjust static pressure. Static pressure tadi apa tadi? PV equal to berapa tadi? Not yet. Maybe next formula. But this correction first. This one is a correction factor is elevation change. So ini by feet, by feet. 1,000 feet, 2,000 feet, 300 until to 15,000 feet change. So the correction based on temperature, plotting. So in the Fahrenheit, Fahrenheit until to 1,000. So the correction will be maxima is 4.89. Okay, let's check how to use. Example 1. Air is flowing through the 75 feet straight duct, which has a size of 36 diameter. Duct size in rectangular shape. The duct is traversed, pressure measured, taken a various cross-sectional location, and average total pressure PT equal to 2 in the water gauge, and the static pressure of 1.75 in the water gauge measured. Determine the air velocity, air flow rate in the duct. Okay, let's check how to use it. Air flowing through the 75 feet straight, and then the duct dimension, and then the PT, total pressure, and then this one the PS, static. Okay, based on the question, we have the PT, PS. Then from formula, total is sum of the PT is sum or static, and then with the dynamic. So the question is dynamic. Just remove PS from the right side to the left side by change to the negative, and then we get the formula PT negative to PS, and then the PV dynamic, dynamic pressure is 0.25 inches water gauge. The air velocity is determined by using the dynamic pressure equation. So this one is a formula. So PV, and then we can elaborate the velocity. So the velocity in the unit of feet per minute, 2002. And then for the airflow, V dot, or sometimes we use Q to mention the flow rate. Okay, the formula flow rate is velocity times to area. Area is by 36 by 12, the area. And then we can get the Q, or the flow rate, air flow rate. So any question here? Ada soalan?
Tak ada, sir.
Tak ada, still easy. So never mind. If you still follow me, it's never mind. But if you still confused but don't want to ask, is the problem, Okay, we go to the example 2. So example 2, we will use the first example, but the question will be asked about other. What is the friction loss for entire length of duct, which is given in previous example 1? Okay, we can calculate by head loss formula, just introduced before. HL equal to L times to CL negative to 100 feet. So after determine the friction factor. Okay, CL, where do you get CL? From duct calculator. Okay, because we are already have in duct calculator, we are already known the dimension, dimension, just plot dimension. Okay, and then we can refer matching the dimension, and then we can get the other information like the air flow volume, friction per 100 feet. So friction per 100 feet, and then they get from plotting 12 times to 36 inch. So just plot here, 36, 36, and then times to 12, and then we can get this one, the this one, the friction. Then the friction given in the duct calculator 0.21. Okay, and then just complete the HL. You can, because length is 75 feet, to analyze. So we can get the HL is 0.1575 inches water gauge. So any question? Ada soalan?
Tak ada, sir.
Okay, I hope you understand. Boleh, Okay, now we go to other condition. Just now maybe condition is straight, dark. Now we change the elevation condition. Okay, this condition is come from the 75 feet length section in diameter 24. Oh, see. So mean the flow is from here. So diameter, duct has this one, the standard condition flowing through. If the duct make 90, okay, this one, 90. Before transition in the, okay. The first is diameter 1 and diameter 2. Okay. The elbow are blah blah blah. What is the pressure loss for the entire section of the duct fitting? 1 feet 12 inch. Yeah. So how much the total of pressure loss? Okay, back to the formula of pressure loss. So we can calculate part by part. So the straight part and the elbow part, and then we sum all part. Yeah. So ada berapa part ni? We can use satu, first, second, third, fourth, fifth, six part in the instrument. Ada 6 six instrument. So every instrument will be contribute to head loss. So how to find out? Ini berapa every ni, and then we sum. Okay, first analyze pressure friction loss in the straight line, and then the transformation, no transformation, and this one is calculate transformation. Dia calculate dulu yang ni, and then in the velocity, semualah in transformation, and then this one is elbow, and then calculate for elbow. How to calculate by elbow? So the calculate by elbow is reducing R from the 18 to 24. So we can get this from table. Table. Still remember mana table ni? Okay. And then total we can get this one from table. Just calculate elbow. So 2 elbow. This one 2 elbow. 1 dan 2. But this one is for elbow. First. Yang reducing elbow. This one is for reducing elbow. Lost strike section, so ada 2 section satu section 24, satu section in the 18 for straight line, and then we sum, head loss. Okay, that's all for today. Any question?
Sir,
Yes.
I mean no question.
Attendant, location?
No question.
Oh, no question. Thank you. Mean you understand lah.
Yes, sir. Yes, sir.
Okay. I hope you can follow. Actually, this one is just implement in from the fluid mechanic into the hatchback system. Sama je. Kadang-kadang what make confusion is when we convert from SI into the what you call a British or imperial. British we call imperial unit. British unit and imperial unit sama. Okay, if you don't have a question, I will try to get your attendance. So maybe if you Yeah, this one. Okay, in week 2, yeah. In the week first, because still a lot number not update in the system, so that's why I don't put your name attend or whether attend or not attend, absent in the first week. So maybe I will put all attend the class in the last week. Okay, let's start to call your name. Chu Jun Kai, are you
Saya,
there?
sir.
Okay. Kartik.
Yes, sir.
Oh yeah, thank you. MD Tanvir. MD Tanvir is Muhammad Tanvir. Are you there? Muhammad Tanvir. Muhammad Tanvir, are you there? No. Muhammad Irfan Indrawati. Okay. Muhammad Izmul Fariz.
Yes, sir.
Muhammad Izzat bin Saleh.
Saya, sir.
Muhammad Umarul Adim.
Saya.
Okay. Next, Muhammad Sazwan. Muhammad Sazwan. Sazwan Zulhilmi. Tak ada. Muhammad Adib bin Muhammad Nur Adenan.
Saya, sir.
Okay. Muhammad Adib Hakimi.
Ada, sir.
Alright. Muhammad Aiman Haikal.
Ada, sir.
Okay. Muhammad Akmal. Muhammad Akmal. Tak ada.
Saya, sir.
Ah, ada. Okay. Muhammad Amin Syafiq.
Ada, sir.
Alright. Muhammad Aris bin Johari.
Ada, sir.
Muhammad Hazim bin Ahmad.
Saya, sir.
Okay. Muhammad Hazim bin Mansur.
Ada, sir.
Muhammad Izzuddin bin Mukhtar. No? Missing tak apalah. Muhammad Mustaqim.
Ada, sir.
Okay. Muhammad Sufyan bin Mazlan.
Ada.
Alright. Muhammad Syahir bin Ma'ruf. Muhammad Syahir bin Ma'ruf. Tak ada Nabil Aiman. Nabil Aiman. Tak ada juga. Nabil Muhammad Syahmi Mu'alib. Oh, satu lagi. Muhammad Syahmi bin Mu'alib tak ada. Muhammad Syahmi ada. Ada. Okey. Muhammad sorry. Nabil Aiman tadi ada. Nabil Aiman yang tak ada ya. Noraiman Naim? Ada. Parani.
Ada, sir.
Okey. Umarul Hakimi. Umarul? Tak ada Umarul. Wan Ahmad Syakir.
Ya, saya, sir.
Okey. Ada nama yang tak saya panggil? Atau ada yang silap dari sini? Boleh cek.
Sir. Syazwan ada, sir.
Sazwan nomor berapa tadi? Sazwan nomor berapa tadi?
8.
8.
Kapan sir?
Okey.
Saya ada sir.
Tu siapa tu?
Nombor 20. Muhammad Syahir bin Ma'ruf.
Okey. Ada lagi? Ada lagi? Tak ada ya? Okey, kalau tak ada, kita tutup kelas ya.
Alright, sir.
Okay, we meet next week on the berapa hari bulan tu?
22
22.
start time
22. Okay. Okay, see you next week. Assalamualaikum and good afternoon.
Salam sir.
Thank you sir.
Thank you, sir.
Waalaikumsalam.